All right, let's see who's here. Happy Friday. Welcome back, suckers. Adrian,
Here.
Monique, Elias, Hector, Raymond, Cassandra,
Here.
Lisandro,
Here.
Valerie, Jordan,
Here.
Carolina, Chris,
Here.
Marialis, Eileen, Leonardo,
Here.
Saul,
Here.
Jose,
Here.
Alexander, Brianna, Imad,
Here.
Lorena, Sophia, E-Man,
Here.
Alan, Perla, Janelle, Martin, Drew, Monique. Okay. All right. Let me start with the most important meal of the day. Okay. So we're going to pick up today where we left off last class. All right. And last class, we were working on the modulus of elasticity and beam deflection. We already finished up with centroids. Those are going to come back. Today we're working on beam deflection. Good morning. Welcome back. So last time, we used our thin 3/4 inch plank that we could not stand on for very obvious safety reasons. So today, we're going to do those same calculations, but snuck into Home Depot and nobody's looking and acquired some 2x4s. Okay. So we're going to try calculating the beam deflection with both planks and joists. What's the difference?
Joist is like in your electrical college.
All right, so it's orientation, right? So when it lies flat, it's a plank. When it stands up, it's a joist. Which one do we expect to be stronger? The joist, okay? Why does the orientation make a difference?
More than is how much the gravity.
More mass. Okay? The mass of the board is, of course, the same. But when we're talking about moment of inertia, right? The amount of mass that matters is how much is between the application of force and the bottom of the object. The thickness of the board matters. And in a joist, you get way more thickness than you do as a plank. So it ends up being stronger. Okay? Which we see in our moment formula, right? BH cubed over 12. Right? The height, the H, is the height of the object perpendicular to the application of force. So if I'm pressing down on the edge of the board, especially this tall board, okay? If I'm pressing down on the edge of this board, this becomes the height. And we talked about this is 5.5 inches thick. 9.5 inches thick. I can remember numbers. Okay. Whereas if I press this way, it's 3/4 of an inch thick. So on the thin edge, I can deflect this with my hand. No problem. Okay. But if I turn it this way and I try to make it deflect, yeah, that's not happening. Okay. So we're going to use our max deflection formula first, okay, because we need to know what the modulus of elasticity is for these 2x4s. Because these are not made out of the same kind of wood, different shape, different consistency, and we have 2 different boards. Okay, so we're going to start out with some deflection. And we use a known weight. In this case, the known weight is 90. Take that floor, got it coming. Hey, if you can't be dramatic early in the morning on a Friday, then what are you doing? I mean, really. All right, so let's review our formula. For delta max, it's FL cubed 48 EI. What's the F? Force, yes, be confident, you're right. It's the force. In this case, what force are we talking about? Yeah, me. Weight is the force that we're talking about here. Okay, who ate my crayons? Is there a Marine in here? Okay. So weight is a force. Okay, in this case, we're going to calculate my weight as our source of deflection here. All right. And this is Madrid. It's 190 pounds. Okay. So that's our F. What's our L? L for gravity. Wouldn't that make it gravity? You guys remember what L is? It is length. But what length are we going to measure here? Okay, so that distance, right, the vertical distance is our deflection. We're going to calculate that. Okay, and we're going to measure that. L here is span. Right, and span is the distance between our supports. So we're going to measure how far apart our supports are here. Did I leave a meter stick over there? No, I didn't. Okay, and to make this easy, okay, these are under 2 meters. So we're going to set our span to 2 meters. Hopefully, Mr. Madrid doesn't break one of these boards because that was pretty embarrassing. Okay. So we're going to start with this one. We're going to do this twice, one for each board. All right, distance span is 2 meters, and we're going to mark this board as board 1. So our L here is 2 meters. Are we off to a good start? Maybe. Because it looks to me like this formula that we've been using is in standard units. Imperial units are made up American units. Is meters a made up American unit? Nope. We got to convert that. Okay. We got to convert it to inches because our deflection is going to be measured in inches. How many inches are in a meter?
72.
It's not 36. A little more than that. The meter is slightly longer than the yard. 78? That's a little too much.
What?
Yes.
39.
So 1 meter is 39.5-ish meters. There is a proper calculation for that. Okay. Now, we've got 2 of these, so we're going to times 2, and that is 79. So yeah, we're close. 79 inches. All right, so we've got our F, we've got our L. We're looking for E. We need I. How do we calculate I again? Yeah, that's right there. I equals GH cubed over 12. Okay, and since this is a plank, it's a 2x4. Since this is in plank, is B the 4 or the 2? The 4, good. Okay, so our moment of inertia is 4, 2 cubed over 12. What's 2 cubed? 2 to the third power. 8. 8 times 4? 32. Okay, over 12. Does that divide evenly? It does not, unfortunately. How many times did 12 go into 32? 2 times. What's our remainder? 8. Good. Thanks, sir. All right, 8 over 12. Does that reduce? Yes, 2. 4 over 6 or 2 over 3. Okay, last thing we got to do. We need to measure our deflection here. Because the only thing we're looking for in this formula is E, not our modulus of elasticity. So we're going to start with our initial height in inches, which is 5 1/4. Double check that. All right, and span. So 5 1/8 is our initial height. All right, I need a volunteer for measurements here. Take a measurement.
Not it.
So you're going to measure the height of the board once I'm standing on it.
It can support your weight.
Oh,
You cried.
it did. Oh, come on. 3 1/2.
Damn.
Yeah, I tell you, Mr. Madrid's not a light dude. Mr. Madrid's not a light dude. Take that, gravity. Okay, it goes down to 3 1/2. So if this is our initial height and this is our final height, how do we calculate our max deflection? We subtract them, and everybody loves subtracting fractions, right?
Yeah.
And I can see the joy on your face already. Okay. What do we need to do here? By what? Cross something? We can, right? We can turn these to improper fractions, which does make it easier to subtract. So we'd multiply the denominator and then add the numerator. What's 5 times 8? Plus 1, 41 over 8. Okay. 2 times 3 plus 1. Okay, so we got 41 over 8 minus 7 over 2. What do we need to add or subtract fractions? Equal denominators. So what's the first number that 8 and 2 both go into? 8. 2 goes into both of them, but we need a number that they both go into. So we can't turn this into a 2, but we can turn this 2 into an 8 by multiplying by what? 4. And if I multiply the denominator, do I have to multiply the numerator as well? Yeah, that's right. Okay, so we've got 41 over 8 minus, what's 7 times 4? 28. And that's over 8. Now we can subtract. What's 41 minus 28? 13. It's close. 13 over 8. 8 goes into 13 one time with the remainder of 5 over 8. Okay. And we've already simplified our formula from yesterday. Our modulus of elasticity is equal to force times span cubed over 48 modulus, not modulus, moment of inertia times max deflection. We already have all these now. So we're going to plug them in and see what we get. Okay, so our force is a very considerable 190. Our span is 79 cubed over 48. Okay, our I is 2 2/3. Our delta max 1 5/8. Who wants to do that in their head real fast? Okay, someone get out a calculator. The numerator, 13,351. Okay. And then.
Oh, wait, hold on.
You got a billion?
Yeah, the first one's 15,010.
15,010. That's a big difference, young lady. Not that I don't trust you, but I'm going to do this calculation too. Yeah, you got to cube the 79.
Yeah.
Okay, so 79 cubed, right? So that's times 79
Oh, I didn't
times
even see the
79 times 190. Yeah, it's 93 million.
I didn't see the-
Oh, yeah, you were right. Bro, I'm out here in my head. You're so dumb.
Okay,
So wrong.
and then our denominator here, 48 times 2 2/3 times 1 5/8. It's 207.48. And then we're going to divide. Okay, giving us 451,500.9, but once you get over 400,000, I think that extra one, you can ignore that safely. Okay. So the modulus of elasticity for this 2x4 is very high. Does that make it resistant to deflection? Yes, it does. Okay. So why did it deflect so much? Yeah, Miss Madrid likes cheeseburgers. Okay, that's why it deflects so much. Okay, I probably should have skipped that breakfast burrito, but I didn't, and I don't regret it. Okay, now I'm gonna jump on it.
Oh, God.
I'm kidding. Relax. We still got to use this for science here. All right. So now that we know our modulus of elasticity, could we use the same formula to calculate an unknown weight?
No.
I mean, yeah.
Technically and actually, yes. It's exactly how traditional bathroom scales work. Okay. They've got a spring on the inside, and when you stand on it, because the mass of the spring and its modules of elasticity are known, when you stand on it, it deflects the beam on the inside, a known delta max. They already know how much weight it will take to deflect it. So when you stand on your grandma's bathroom scale, right, it's got the needle in it, right, and the needle starts moving, it's exactly what's going on. You're applying a force to a known spring on the inside, and it's achieving a pre-calculated delta max. They just label the 9 numbers on it so that they know, you can know what your weight is and get the press, just like the rest of it. It's for Americans, and that's how we do it. Okay, if I wanted to calculate somebody's weight, what would I have to do here? Yeah, we have to switch the force to the other side. Okay, so exact same formula, but we're going to rewrite it. All right, that's what we're going to be working on this period. On the Google Classroom is an assignment. It's a worksheet for you. As usual, we're going to copy problems down into our notebooks. Okay, do the work and submit a picture. Okay, so if you do not have your laptops yet, go ahead and grab your laptops, log into the Google Classroom, and we're going to do some work.
Oh, I couldn't read it. I thought it said press. The eyes are on.
I know, Mr. Martin offered.
Hey, I'm left on the list. That's all I gotta say.
But he's covered different.
I said y'all foul. And we just
And
left
he's
with
covered
it.
some lit. Those are things that he did. So I don't think that's really clear with you guys, so I'll probably give you some kind of
We're just 2 weeks left.
Yes, there's 2 weeks, not counting today, you have 9 days of school. Because next Friday is a non-student day. And remember that the last 3 days of school are finals, those are not school days, those are test only days. So really, in terms of actual schoolwork, you have 6 days of school left.
Oh, I'm sure.
Yeah.
I got a bunch of missing assignments for science.
What do you have for science?
But stay.
You're making me concerned.
Yeah.
But it could be worse. It could be Miss Maya.
I'm not. What are you talking to?
Miss Maya's pretty cutthroat about those late assignments.
It's okay.
Miss Daly should still work with you.
Yeah, like she let me turn in assignments from like August when I wasn't even here, but it's like class agreements. Yeah.
That's good. Every point counts. And so I haven't pulled grade tests in this class because at least in this class, you guys are killing it. So, yeah, I don't want to be depressed. So I just, everybody's got an A in here. I'm so happy.
You know?
Yeah, everyone in the period has an A. This is my only period that does not have any failing students.
You know how you left and like Miss Daly came in and like she made me and Lizanto do like we were partners. She made us do like a what was it like we had to draw like I forgot. We had to draw like a place. Like we had to pick a place and we picked like a vet, like an exotic vet for like tigers, right? And then on the drawing we put like underground there was like cockfights. She got so mad. That was so fun.
Oh my gosh.
Yeah, I actually yeah. Well, I want to get into one.
Oh yeah, super secret.
You guys had like 12 turtles die. Yeah. one laptop. All right. I gotta write this down.
I say me. You're like, oh, you're putting it on the like,
Oh, hey. Oh, dude, I see that shit. It's not when Joseph and found him on this thing. You ever play like a Lego game? Like a Lego Batman?
Yeah.
Oh my god, that was my stuff back in the day.
Yeah, the first 3 Lego Star Wars were amazing.
Oh yeah. So iconic.
Okay,
Hey.
so we calculated, and by we, I mean mostly me, the modulus of elasticity for board 1, which means this one's ready to go. Now you guys are going to talk me through the process of the same thing for board 2. No, change the measurements.
Wait, oh yeah.
All right.
Thing 1, thing 2, 3. Is that you? Oh, damn.
Okay. To calculate modulus of elasticity, what do we need to know? The force, the span, the moment of inertia. Well, modulus of elasticity is the E. We need to know delta max. We need to know our max deflection. Okay. So my weight has not changed. So we're going to keep that one. But the span changed. What should we set the span to?
The length is 100.
100?
Yeah.
100 inches?
Yeah, so it's like this way.
Okay, that would make it pretty convenient. However, make the math nice. But we already know from our discussion on moment of inertia and last week, earlier this week, when we were talking about beam deflections, that the longer your span is, the more deflection you get, right? So if I was standing on this, and we put this between 2 tables, and I climb on top of this, okay, I'm going to go right through it, right? It's barely going to support me at all. But what if I drag this table over here, and I only left 6 inches of gap? Would I be able to get on that?
Yeah.
Probably. It's going to deflect, right? It will deflect at the same rate, but the amount of deflection that I would get is much, much lower because the span is shorter. So when I stood on board number 1 and it began weeping, that was set to 2 meters of span. In the interest of safety, if I'm going to get on another board, should we have a longer span? Probably not. What should we set it to? Probably a lower one. So our last span was 79 inches. What do you want to try for this one? 50? Okay. We'll leave the stack of books right here. We'll scoot these over there. To be slightly dramatic about it. All right. Okay, so that's 39.5. That's 10.5. Okay. And we set our span to 50 inches. We're gonna hope for the best. So our force has not changed. Our L is now 50 inches.
What is that?
Did our I change? Did our moment of inertia change? If that was a 2x4, and this is a 2x4, and that was a plank, and this is also a plank, did our I change? No, they're the same size, same shape, same orientation. So our I is still the same. What was it? What was our I last time? Please let it be in somebody's notes. Right? So I equals base height cubed over 12. And what did we get for that calculation for board 1? No, that was our span. That was our L. Nobody wrote it down in their notes. You guys are embarrassing me. What did we get for I for board 1?
I mean, it was like 4,000.
Okay, so our base here was 4. Our height was 2 cubed over 12, giving us 32 over 12, which reduced to 2 2/3. There we go. So we're going to use that one again. It's the same shape, so we get to use the same moment of inertia. And now we need our max deflection. So we're going to measure our starting height right here in the center. And that is like 5 even.
7 minutes. 7 minutes.
Okay. Ready to volunteer to come up? And we'll see what happens this time.
I gotta take notes now. You know.
Yes. Yes, you may.
Axis is like AX equals.
Reduce the span, you reduce the deflection. So before I lose my balance and break an ankle, someone go measure this.
All right. Oh, like right now? Oh.
Yeah.
It's like 4.5.
Is it like 4.5 or is it 4.5? Accuracy counts.
Yeah, it's 1/2.
Okay.
I think.
Killing me, Smalls. Okay, so our new deflection is 4.5, which means our delta max is